So, good evening, everybody. As I say, I hope you're all well. Tonight we have a very welcome return of Dr. Fred Stevenson. He's going to talk to us about the farthest objects in the universe and how far can we look to see them. So, Fred, over to you.
Okay, thanks Derek for that introduction, and I will start to share my screen as usual, and you should hopefully be able to see my PowerPoint presentation before too long. I'll just get this onto the first slide. How's that? Does that look
Yeah,
okay?
We can see it, that's fine.
That's great. Yes, so my talk tonight is going to be, it's really a continuation, I think, of the first talk I gave to Nastro about the distance scale in the universe. And tonight I'm going to concentrate on the very farthest objects we can see out in the distant universe and try to clear up some of those cosmological conundrums that we often come across, particularly when we get to objects that are very, very far away, such as what does the meaning of distance really correspond to when we're looking so far out in distance as well as simultaneously back in time. And so we'll have a look at all of those things as we go along this evening. So let's just start at the beginning with a little bit of introduction, which I'm sure you're all very familiar with, and that's to have a look at our Milky Way galaxy. This is our home galaxy that we live inside of. And so, of course, we live on planet Earth orbiting the sun, which is one star amongst several 100 billion stars that make up this huge system of stars that we call a galaxy. Our own galaxy, we call it the Milky Way galaxy because of the appearance on the night sky of the Milky Way, which is where we're looking into the plane of our galaxy, which is a so-called spiral galaxy, which corresponds to a disk-type galaxy with a central bulge and a relatively thin disk of stars, which you can see in this first slide here. I'll get my laser pointer on so I can point things. This is a side view of the galaxy on the right, and on the left we have a plan view of the galaxy. And you can see it is like a gigantic Catherine wheel, roughly 100,000 light years across. So it's a huge system containing that incredible number of stars and other planetary systems. And the whole thing, as its appearance suggests, is rotating around its center of mass. And it takes over 200 million years to actually spin once on its axis, a remarkably long, almost geological timescale, really, even though the sun with the planets is orbiting the galaxy, as are all the other stars. We happen to be moving at roughly 230 kilometers a second with respect to the center of the galaxy, with this tremendous speed. But it gives you some appreciation for how large the galaxy is when you think that even at that speed, it takes you over 200 million years to actually orbit around the center of that system. So even on the scale of the galaxy, we're looking at huge distance scales, and even at the speed of light, it would take us 100,000 years to actually travel across the width of our galaxy. That's what a light year essentially means. It's a unit of distance, which corresponds to 10 trillion kilometers or 6 trillion miles. But it also refers to a time scale in that one light year is the distance light travels in 1 year of our time scale. So tremendous distance. Of course, the nearest star to us, Alpha and Proxima Centauri, are roughly 4 light years away. So 4 years at the speed of light, even to get to the nearest star. And so interstellar travel, let alone intergalactic travel, is probably way off in the future. So let's move swiftly out of our galaxy and look out into the night sky. And of course, the first large comparable galaxy to our own is the famous Andromeda galaxy. And this is the system of stars, or the object in the night sky, that really began the science of cosmology, the study of the universe as a whole. Up until the 1920s, no astronomers had proven that anything really exists beyond the stars we can see in the night sky. And those stars become more numerous as you look through more and more powerful telescopes. And they just seem to go on and on and on. And astronomers didn't really know if that system of stars had a boundary, and if so, were there other systems of stars that lay beyond? This was an ongoing question in astronomy for many, many decades. It wasn't until the 1920s that Edwin Hubble showed that this beautiful spiral structure we see in the constellation of Andromeda, which was called the Andromeda Nebula originally because it could have been a nebula in our own galaxy, which is a cloud of dust and gas within our own galaxy. There were theories that it might be a planetary system in formation where you have a central star forming and the disk of material is a disk of dust and gas out of which planets might be forming, which is actually how we think planetary systems do form. But the interesting thing was Hubble was around in the early 1920s or the late 1910s when the Mount Wilson telescope had been opened up in California, and that was the first telescope capable of zooming into small areas of this misty object, and it resolved into individual points of light rather than remain a sort of milky glow. It became a mass of individual points of light. In other words, it was made of stars. And by comparing the brightness of those stars in this object to stars that you might see in the foreground here, all of the stars in this picture, of course, that you can see individually, they're all stars within our own Milky Way galaxy that we're looking through on the way to Andromeda. The stars in Andromeda itself are very, very faint, impossible to see in a picture like this, but with very large telescopes you can do. Comparing the relative brightnesses gives you an indication of distance, and Hubble worked out using a type of variable star in this galaxy that he knew the intrinsic brightness of. He could work out the distance to this Andromeda Nebula, it's called, and showed it was about 2.5 million light years away, or at least that's the currently accepted figure. He got a different figure because of everything was at a very much beginning phase in terms of cosmology at the time, but we now know that his answer was roughly correct, and we now talk about Andromeda being 2.5 million light years away. That puts it way outside our galaxy. Even the largest estimates of the size of our galaxy, even if it was a few 100,000 light years across, would be nowhere near this tremendous distance. And so by looking at the angle on the night sky, this is about 3 degrees in angle across on the night sky. To have such a large angle and such a large distance, because the object itself must be enormous. And it does indeed turn out, if you do a little bit of trigonometry, you can show that this object is over 100,000 light years in diameter. It's of comparable size to our Milky Way galaxy. It is another Milky Way galaxy, essentially. So that was Hubble's first great discovery, to show the nature of the so-called spiral nebulae were in fact other external galaxies. And this really, as I mentioned, began the science of cosmology. We could then start to draw maps of our local surroundings in terms of cosmological distance scales, scales of millions of light years, and you can see this is a map showing the Milky Way situated at the centre, because that's where we happen to live, and we've plotted Andromeda on here, just over 2 million light years away on this scale, and this is a map of our so-called local group of galaxies. There is another large-ish galaxy in the local group, the Triangulum galaxy, that's marked there in the constellation of Triangulum. I'm sure some of you have seen the Triangulum galaxy through your telescopes, and it is a smaller type of so-called spiral galaxy. As well as those 3 spiral galaxies, there's a few dozen very small so-called dwarf galaxy systems and irregular galaxies. 2 of the larger dwarf galaxies actually orbit the Milky Way. They're the famous Magellanic Clouds, which you can see from the southern hemisphere in the night sky. They're the 2 brightish blobs next to the Milky Way here. They're a couple of 100,000 light years away. On this map, of course, they look very close to our own galaxy. and they will be interacting with our galaxy because of their mutual gravitational attractions, and essentially they will be orbiting our Milky Way galaxy in some form and may one day merge with us, as indeed is the Andromeda galaxy, and possibly most of the systems of stars in this group will eventually merge together to form an enormous so-called elliptical galaxy, which is the other major type of galaxy that we find out there in the wider universe. So we can easily, well, not that easily, but it's definitely feasible to measure distances to these local galaxies using stars within them that we know the properties of. And then we can look beyond our local group, of course, to other groups of galaxies that are in our relatively nearby neighbourhood, cosmologically speaking. The next group of galaxies we come to in the direction of Ursa Major on the night sky near the Plough is the M81 group. These two galaxies are visible through a pair of binoculars on a nice clear dark night and make very nice imaging targets, as I'm sure your members have seen again. But the larger of these two galaxies is a beautiful spiral, M81 or Bode's galaxy. That's similar in structure to our galaxy in Andromeda, and the galaxy on the right is M82, the next object in Messier's famous catalogue of fuzzy objects on the night sky. You can see on the right there is an example of a so-called starburst galaxy. You can see these strange filaments coming out of the nucleus of the galaxy, which is clouds of dust and gas being expelled by numerous supernovae explosions that are going off in M82. A burst of star formation is going on there, and that's been triggered by, again, their relative closeness has caused gravitational interactions, and those forces have triggered the collapse of gas and dust clouds in M82 to increase the star formation rate. There's also, of course, a lot of star formation going on in M81, and all spiral galaxies have ongoing star formation in their spiral disks, as indeed does the Milky Way galaxy, of course. There's places like the Orion Nebula that we mentioned earlier, which is our nearest region of star formation in the Milky Way. So this pair of galaxies are roughly 12 million light years away. They're smaller and fainter on the night sky than Andromeda, of course, because they happen to be maybe getting on for 5 times as far away, which is quite remarkable. So the light left these galaxies 12 million years ago that we now receive in our telescopes as we look at them in the night sky. We can, of course, continue farther and farther out, and we get to beautiful systems of stars such as the famous Whirlpool galaxy, again near the Plough on the night sky, just below the handle of the Plough, depending on which way up the Plough is, of course, in the night sky. M51 in Messier's catalogue, and it happens to have a distance of around about 24 million light years, although that figure does vary depending on what reference you actually look at. But I think the most recent estimate for the distance is somewhere around about 24 million light years. So this particular galaxy, I'm sure, again, most of you will have seen this galaxy through your telescopes. It might be difficult to see through binoculars, this one, but a reasonably small telescope can pick up this galaxy. And actually, you've probably noticed that, in fact, it's two galaxies side by side. The galaxy on the right, this blob on the right, is actually an elliptical galaxy. It's a huge galaxy of stars in its own right. And these two galaxies have gravitationally interacted and drawn each other together. And it's triggered an enormous burst of star formation in the spiral galaxy. You can see all of these pink regions dotted around the spiral arms, like a string of pearls, if you like, around all of the spiral arms in the galaxy. It's remarkable Hubble image of M81. Each of those pink regions is another huge version of the Orion Nebula that we see in our galaxy. So lots of ongoing star formation, again, triggered by this gravitational interaction, and beautiful, well-defined spiral pattern, another signature of gravitational interactions. And so we're out to a distance here of about 10 times Andromeda, but with powerful telescopes we can still see these galaxies in remarkable detail. In fact, we can see these galaxies in more detail than we know about our own galaxy, strangely, because of the fact we live inside our galaxy, right in the plane of the disk of our galaxy. It's actually very difficult to work out the structure of our galaxy from within because of all the absorbing dust clouds that lie in the plane of the galaxy and obscure the view of the stars beyond through the plane of our galaxy. But by looking out of our galaxy, out of the plane, away from the Milky Way on the night sky, we can see out into the distant universe and see entire galaxies such as this one, M100, beautifully seen there, almost face on to our line of sight. So we get a beautiful plan view of that galaxy and we can see it in extraordinary detail. This is an image from the Mount Lemmon Observatory in Arizona. M100 is the 100th object in Messier's catalogue, of course, and this is a galaxy in the constellation of Virgo, close to the famous Virgo cluster of galaxies, where we have a huge swarm of galaxies clustering together because of mutual gravitational attractions. This galaxy happens to be 55 million light years away or thereabouts, and this galaxy is almost at the limit where we can zoom in and see individual stars that we know the true intrinsic brightness of, so-called standard candles. It was one of the Hubble Space Telescope's early projects. One of its prime objectives was to carry out the work of Edwin Hubble up to the modern day and use standard candles in these galaxies much farther away than Hubble could access in order to work out accurate distances for them. And this is an early Hubble image showing an individual so-called Cepheid variable star in the disk of M100. And you can see, if you magnify up this little box on the right, you can see within that box there is indeed a source of light, and its light is varying from one box to the other. It's getting brighter and then it's getting fainter, and then if you wait long enough it'll get brighter again. And it's a type of variable star known as the Cepheid variable, named after the classic prototype of that type of variable star, which happens to be in the constellation of Cepheus. The remarkable thing about Cepheid variables, it was discovered by Henrietta Leavitt back in the 1910s or thereabouts, where she looked at stars in one of the Magellanic Clouds that we mentioned earlier, and she saw these stars varying. And because they're all at the same distance, being in this cluster of stars, the small Magellanic Cloud, they're all at the same distance, and so any change in their observed brightness corresponds to the actual change in brightness. So brighter stars in the small Magellanic Clouds are intrinsically brighter than fainter stars in the small Magellanic Clouds. That's not true on the night sky in general, of course, where a bright star could be a very bright star far away, or it could be a relatively faint star very nearby, because you don't know the distance. But if you know everything's at the same distance, then you can compare brightnesses to get relative brightnesses very accurately. Now, the interesting thing she found was that for this particular type of variable star, the longer the period of variation between the brightness and the faintness and then the brightness, that period got longer and longer. The stars themselves, their peak brightness actually became brighter and brighter, and there was a direct proportionality between the two. And so it showed that these stars, once you measure their period of brightness, once you've got this calibrated sample in the Magellanic Clouds, you can find them in a very distant galaxy like this one, and all you have to do is measure the period of variation in brightness, and then you know the true intrinsic brightness, and then you can compare the brightness in these images to nearby examples, and the comparison of brightness will tell you the distance, because of the way things farther away obviously get fainter, and they get fainter by the famous inverse square law, 1 over the square of the distance. And so if, for instance, you looked at these Cepheid variables in M100, and they were, say, 10,000 times fainter than the Cepheid variables in the Magellanic Clouds, then you know they would have to be 100 times farther away, because 100 squared is 10,000. And then you would know that they were 100 times the distance to the Magellanic Clouds, which would take you from 200,000 out to 20 million light years. So these stars must actually be fainter, a bit fainter still compared to that, because this galaxy, as we saw, turns out to be over 50 million light years away. But that's the basic principle. You can see these things in galaxies that you know the true brightness of, and by comparing them then to nearby examples of known distance, it gives you the distance to the galaxies. The problem is, of course, you can only use that to go so far out, and then galaxies become too far away to see individual stars within them, even with the Hubble Space Telescope, and even with big ground-based 10-meter diameter telescopes. So then you have to use other distance indicators. And you can also utilize Hubble's second and greatest discovery, where he discovered, of course, that as you go farther and farther out, if you study the light of the galaxies according to their spectra, using a spectroscope, you can measure the spectral lines, the so-called absorption lines in the spectrum of light from galaxies. And as they go farther and farther and farther away, what he discovered was that the spectral lines become more and more redshifted. This is the famous redshift effect in cosmology. Now, the interesting thing is, of course, if you look at Andromeda, the nearest galaxy, the nearest big galaxy to us, I mentioned that we're coming closer to Andromeda and we will merge eventually. So if you look at the spectrum of Andromeda, it actually has a small blue shift. If objects are coming towards us, their light is blue shifted. But that's because they're close enough together, those galaxies, to overcome the tendency for the universe to expand, as Hubble discovered. And when you get very far away, the expansion wins out, and all galaxies beyond our local group actually show a so-called redshift. If you like formulas, there's a simple little formula for the redshift here. This is really the definition of redshift. It's defined as the ratio of the change in the wavelength of light divided by the emitted wavelength of light, or what the wavelength should be if the light were at rest, or the object emitting the light were at rest in a laboratory. For instance, we've got this nice red hydrogen line here, might be the hydrogen alpha line, say, in the red part of the spectrum. So we know by studying hydrogen gas in a laboratory, physicists have measured the wavelengths of these lines to incredible accuracy. And so by measuring that difference in wavelength from the rest wavelength to the moving galaxy wavelength, we can work out the difference, just subtract the two, divide by the original wavelength. That gives us what we call the redshift. And you can show, using the idea of a Doppler shift, which was where Doppler studied sound waves, but he showed that as a source of sound waves moves away from us, the pitch of the sound gets lower, the frequency is reduced, or the wavelength effectively gets longer, the pitch of the sound goes down. That's the Doppler shift. If a source of sound is coming towards you, you get a higher pitch. That's basically where the redshift comes from, if we think of it as a Doppler shift. And the formula for the Doppler shift is that ratio, the change in wavelength divided by the wavelength, is just the ratio of the speed of the object emitting the waves divided by the speed of the waves themselves, which in this case is the speed of light, which is always given the symbol c. So there's that little formula there, which is very useful, that comes from a Doppler shift. Now, in cosmology, the expanding universe isn't quite the same as a Doppler shift. It's caused by the expansion of space itself, and galaxies are moving away from us, not because they're moving through space, it's because the space itself is growing larger. The scale of the universe is growing larger as time goes on. But for small redshifts and small speeds, this formula is very accurate. As long as you're at small speeds relative to the speed of light, you can use that formula quite happily for calculating the speed of galaxies away from us, say. When you get to very high velocities, the Doppler shift formula isn't as simple as that. You have to take into account relativity theories, of course, which we might come back to later. But let's have a look at Hubble's great discovery in a little bit more detail. This is a famous graph of his, well, not actually his data. This is a more modern version of the so-called Hubble diagram, where you can clearly see the effect he discovered, where the speed of the recession of galaxies increases directly as their distance increases. That was the most important effect Hubble discovered. It wasn't just that all galaxies showed a redshift, but there was this very specific relationship between redshift and distance, in that the two were directly proportional to each other. And you can see on this graph that as the velocity inferred from that simple Doppler formula increases, then the distance increases, and the velocities get very, very large as you go to large distances. These are in millions of light years, so we're talking huge distances here. We're going 300, 600, 900 million light years, almost 1 billion light years we would be out here. And when you're out there, galaxies are moving at about 20,000 kilometers per second away from us. At the top of this scale, 30,000 kilometers per second, that's 1/10 of the speed of light. So these are tremendous speeds. These are bigger speeds than had ever been measured for anything moving in the universe at large in the whole of history. So it's no surprise that these results were very carefully scrutinized originally, and a lot of people found it hard to accept, of course, that this was actually a real result, and maybe these redshifts were caused by some other reason rather than movement or expansion. But this has stood the test of time, and particularly because general relativity, Einstein's remarkable theory of gravity, is such a well-founded theory and passed all observational tests, then we accept now that the redshift of galaxies is caused by the expansion of space because of the energy and the energy fields within that space, exactly as predicted by Einstein's beautiful field equations. So this expansion effectively can go to very, very, very large speeds as you go out to very large distances. And you can see the relationship is very tight. So in terms of measuring distances to galaxies, once we have this relationship established, it gives us a really good way of measuring distances, because if we can measure the spectrum of a galaxy, measure its redshift, and then we can use this graph as a sort of calibration, if you like, to just read off the distance for a given redshift. And so we can turn the thing around, and rather than have to work out distances for galaxies using standard candles, which is very, very difficult, but that's what we have to do to plot this graph in the first place. We have to measure the distance and measure the redshifts or velocities and plot these points. But once we have the graph, then all we need to do to get the distance is measure the spectrum, get the redshift, and we can read off the distance from the graph. And so we can, once we get to very great distances, we can do that quite accurately. At small distances, remember, we have galaxies that are close together can overcome the tendency for expansion. They can build up so-called peculiar velocities like our galaxy in Andromeda is doing. And that gives rise to the scatter on this graph in a vertical sense. And so you can see that at small distances, these gravitational speeds, if you like, can overcome expansion and therefore lead to errors. You'd have to work out those distances using the standard candles. But once you get out to a few 100 million light years, the expansion speed is way more than any gravitational speeds over and above that. So you can use the redshift as a distance indicator. And so that's what we do when we do so-called big redshift surveys. We look at fields of galaxies on the night sky using powerful telescopes. We can measure tens of spectra in a given field all at the same time, measure lots of redshifts, get lots of distances, and plot maps of the large-scale structure of the universe just using redshifts. So that takes us beyond the local group and into the realm of the clusters of galaxies. This is a beautiful, relatively nearby cluster, the Fornax cluster. Happens to be at about 60 million light years away. You can see a whole group of beautiful elliptical galaxies. There are spiral galaxies. There's a beautiful barred spiral galaxy down in the bottom right-hand corner here. We can use the Hubble relationship to go out to clusters such as the Coma cluster. That's at about 320 million light years away in the constellation Coma Berenices. That's a large field of view on the night sky, a 2-degree field you can see there, containing literally thousands of galaxies that are within this immense cluster of galaxies. So you need a wide-angle telescope to get all of that in the same field of view, of course. So you don't need powerful telescopes as such to see these things. You need a lot of light grasp. But because they're so huge intrinsically, even though it's 320 million light years away, it's still 2 degrees across on the night sky. It's probably several tens of millions of light years in diameter, the actual cluster itself. And just another example, there's the beautiful Hercules cluster, part of the so-called Hercules supercluster of galaxies, and that's roughly 500 million light years away. So these distances are well within that Hubble diagram that we saw on the graph a few slides ago. So if we plot a 3-dimensional map of all of these galaxies and their various clusters and superclusters, this is the sort of thing we find. Remember, we don't necessarily have to measure distances for all of these points, but we do have to measure redshifts. And then the redshift gives us the distance, and we can plot a beautiful diagram like this of the large-scale structure of the universe around us. And we can see the local group we saw originally, our galaxy in Andromeda in the center here. We have the Virgo cluster that we mentioned, a near neighbor, big cluster of galaxies, 50 million light years away over here. The Fornax cluster we saw a picture of is probably, I think, this blob to the left here. So they're relatively nearby in terms of large-scale structures. We go into the so-called local supercluster, which links to the Centaurus clusters. And then we saw a picture on the previous slide of Hercules, that the Hercules cluster is up here, about 500 million light years away. You can see this remarkable foam-like structure of walls and sheets of galaxies surrounding voids where there are very few galaxies, relatively few galaxies. This is the large-scale structure of the universe, and this is the sort of structure that is expanding as time goes on, even though within clusters and groups on those much smaller distance scales within these clusters, the galaxies can actually be falling inwards, which of course is what grew this structure in the first place, out of an expanding foam, if you like, of a much smoother distribution of material from the Big Bang. This structure had to condense, if you like, out of that expanding material, and that was because of the nature of gravity, of course, has overcome the expansion to form this structure. So it's a rather beautiful large-scale structure of the universe that we see around us in all directions. One or two conundrums that we must talk about, just to emphasize this idea of expansion. And there's a lot of misconceptions about the expanding universe, and one of them is that people always ask, what is the universe expanding into? Well, in terms of modern cosmology and using Einstein's general relativity theory, we shouldn't really think of the galaxies as expanding into anything. I mentioned earlier that we should think of the expansion of the universe as the expansion of space, and that space growing bigger takes the galaxies with it. And so we should think of galaxies as being fixed in an expanding space, just like the galaxies we see here on the surface of this balloon. This is the famous balloon analogy. But the idea is that the universe is the surface of this balloon, a two-dimensional surface. So we're talking about a two-dimensional universe. And I know our universe is actually three-dimensional in terms of space, but it makes it a lot easier to conceptualize what's going on if we reduce it down to two dimensions like this. And we can see how we can get a space full of galaxies. The galaxies are everywhere within that space. There are no boundaries because it's a spherical balloon, say, and so there are no edges to that universe. There's just space and galaxies within the space. And as the universe gets bigger and expands, there's more space, but the same number of galaxies, interestingly. But they all get farther apart. And so depending on which galaxy you live in, it doesn't actually matter which galaxy you live in. You will observe all of the other galaxies getting farther away from you as time goes on. And that is the basic Hubble effect, if you like, the Hubble law. And galaxies that are farther away, because there's more fabric to expand in a given time between you and a more distant galaxy, they will appear to be moving away from you faster. So as you go back in time, you can think of another diagram to the left, and the balloons can get smaller and smaller and smaller. And then you go down to the so-called Big Bang, which corresponds to roughly 14 billion years of time ago, when all of this material and all of the space within that universe is shrunk down to a tiny, tiny volume compared to what it is now. But the galaxies or the material within that volume, within that space, filled all of that volume. There is no pre-existing void. It's a whole self-contained entity that is growing larger as time goes on at the current time. In the future, of course, the expansion may halt and could even recontract, but that's a different phase in the history of the universe. So if we have any questions about that later, of course, we can come back to that. But let's move swiftly on and just talk about some of the most distant galaxies in the universe then. If we go beyond the use of standard candles, and we can use redshift as a distance indicator, we're basically asking what are the highest redshifts that have been measured? And we go out in distance and back in time a very, very long way, and we talk about the so-called high redshift universe, where the expansion speeds are very, very great. And we can utilize another one of Einstein's beautiful predictions from general relativity, that is the gravitational lensing of light, which was a prediction of general relativity, even decades before it could be used in astronomy as it is today. The effect was proven famously by observing a total eclipse of the sun when the moon is in front of the sun in the daytime sky, and you can see stars around the sun, which would otherwise be visible at night. But because of the presence of the sun, the stars are in slightly different positions. You could imagine the massive object in this diagram as being the sun, and this green object out here being the Earth, and a distant star beyond the sun. Its light is bent in the gravitational field of the sun, and therefore when the light comes to us, it's coming from a different direction, and so the apparent position is shifted outwards from its original position. And that's the effect we're looking for stars around the sun during eclipse, that was famously observed by Sir Arthur Eddington back in the 1919 total eclipse of the sun. It wasn't until the 1980s that this effect was seen on a much, much larger scale, cosmological scales, looking at galaxy clusters and galaxies beyond those galaxy clusters. In that case, the massive object here is a whole cluster of galaxies. So we have huge amounts of mass, tremendously vast gravitational fields, and beyond you have other galaxies. And as their light comes through the cluster, the gravitational field of the cluster changes its direction, and we can get a shift in the position of the galaxies. Of course, you might ask, well, if we didn't know those galaxies were there beforehand, how do we know where they're supposed to be? So how do we know they've actually changed their position? Well, the interesting thing is they don't just change position, they actually change their shapes as well. And you can see if everything were perfectly in alignment here, then the light from this source on the left would be bent around the object at the top and around the object at the bottom, and it would split into two. But it could just as equally well go around the sides of the object and split into four. And in fact, if it goes around all of the sides of the object, it would be split into a ring. This is a so-called Einstein ring, where you could get a ring of light around a foreground galaxy or cluster. And that's an effect that has been looked for and now has actually been observed, as we will see. But if everything isn't in perfect alignment, then the ring that is predicted here would split into so-called arcs. And that is the beautiful effect that was seen dramatically in another one of the Hubble Space Telescope's early images of galaxy clusters. You can see this entire cluster of galaxies, and it's covered in these strange arcs of light. These arcs of light are distorted or gravitationally lensed images of galaxies that are way behind the foreground cluster. And so we have gravitational lensing going on here. It's a remarkable effect. If only Einstein could come back today and see these remarkable images of his prediction in action effectively, which he thought would actually be virtually impossible to observe. This particular galaxy cluster is in the famous Abell cluster catalogue and is Abell 2218. If we look at the redshift of the spectrum of the galaxies in the cluster, it has a redshift of about 0.2. That means those galaxies are moving at roughly a fifth the speed of light, because 0.2 is a fifth. That's not too fast, so we can use the linear Hubble diagram, and we can use the Hubble diagram then to read off the distance. And if we do that, we find these galaxies are actually at about 3 billion light years away, 3 giga light years. That's 3 billion light years. So we're off the top of that Hubble diagram we saw earlier, but we're still in the region where we expect it to be linear with uniform expansion. So remarkably huge distance, and that's the foreground cluster. Some of these arcs of light is coming from galaxies probably twice as far away, at least, beyond the galaxy cluster. So the beautiful utility of gravitational lensing is that, as well as distorting the images of these distant galaxies, is not necessarily a good thing. The good thing is that if you remember back to that previous diagram, you get a focusing of the light. And so these images are actually containing much light. They're much brighter than they would be otherwise. And that's the really important thing in terms of cosmology, because it makes more distant galaxies even brighter than they would be if the lensing cluster wasn't in the foreground, which is absolutely fantastic. It allows us to see much more distant galaxies much more easily than would otherwise have been the case. It's like having a vast, huge natural telescope lens 3 billion light years away, and it's sending us extra light in our direction. Absolutely incredible. This is my favorite gravitational lens image, showing the smiley face gravitational lens, which has a fairly boring catalogue number from the Sloan Digital Sky Survey, J1038 plus 4849. That's the coordinates on the night sky, effectively, right, ascension, declination. The beautiful arcs of light. You can see here sort of almost a distorted image of a spiral galaxy there being spread around these foreground elliptical galaxies in a cluster, which make the eyes of the smiley face. If we measure the redshifts of the galaxies and the arcs of light, we find redshifts of 0.3 and 0.6, corresponding to distances about 4.5 and 7.5 billion light years away. So this is an interesting distance, of course. These galaxies in the foreground here 4.5 billion light years away. That means the light we're now receiving from those galaxies left those galaxies just about as our solar system was forming. Ancient meteorites that we have samples of, like the one that landed, I think it was down in the Cotswolds somewhere a few weeks ago, that was a carbonaceous meteorite, roughly 4.5 billion years old from the birth of the solar system. The light from these galaxies has been traveling through the universe for all of that time until it lands in the telescope that took this remarkable image in the here and now. These timescales are so vast that we're looking back significant fractions of the age of the universe since the Big Bang event, and so we can no longer actually assume that Hubble law is going to keep going linearly and continuously. And so we can't so easily translate these redshifts into distance when they get very large, because the thing is, the expansion rate of the universe will certainly not be uniform over those sort of time scales. It might be uniform or the same as it is now, going back a few 100 million years or even 1 billion years. But when we start to think of billions of years, we have to start to take into account how we think the universe has changed in its expansion rate. So then we have to start to use full-blown general relativistic equations in cosmology to translate the observed redshift into a corresponding distance. And that starts to get very technical, but it also starts to get very interesting and quite mind-boggling, actually. We start to have to get to grips with what these distances really mean. So this slide I'm looking at now really encapsulates the crux of tonight's talk in terms of how we measure distances in cosmology and how we convert, say, an observed redshift into a distance. Because really, at the end of the day, we don't actually measure distances. All we measure are redshifts for these very distant objects. That's the only measurable thing we have. Well, apart from brightness, of course, the brightness on the sky, and from the spectrum, we can deduce other aspects of the galaxy, such as how many stars it might be forming, star formation rate, colours, etc. But one of the main parameters we can measure very accurately in cosmology is this redshift. But because of the expanding universe and the idea of when we look out in distance, we simultaneously look back in time, it becomes ever more difficult to translate that into a meaningful distance. So in cosmology, we really have to start to think about several different types of distance. As you can see in this graphic here, we've got a space that's expanding and a time scale up here. And when this photon of light ends up in our galaxy on the right, the galaxies are very far apart because of expansion. But when it started in the middle, they were actually very close together because it was a long time ago and the universe was very much smaller. And so this is how light travels through an expanding universe when the expansion rate is also varying. There is no limit to the speed at which space can expand in general relativity. We are limited by the speed of light within space, according to Einstein's special relativity. And that's the only restriction. We can't exceed the speed of light by traveling through space, but space itself can travel at any speed effectively. And so we can think of the distance these galaxies are apart just as the light arrives that we now see, but we can equally think of the distance they were when the light left the galaxy in the first place. And those distances, as you can see in this illustration, are quite dramatically different, and can be quite dramatically different. I'll try to stop this graphic, which I worked out earlier I can do by just doing that, I think. Just do a right clicker, otherwise it tends to send you a bit dizzy. But you can see here, at 3 billion years of time that is elapsed, the photon is on its way to our galaxy It's not necessarily that far away from us, but because the space is expanding so rapidly, it could actually be getting farther away from us at this point. And in fact, if you follow the graphic on from here, it does. Because of the expansion, the light itself can't make any headway towards us. It's like going up an escalator the wrong way. And so we have these different distances. The distances we normally talk about is simply the so-called light travel time distance that we've talked about previously, where we think of the amount of time it's taken the light to travel between one galaxy and another. And if we multiply that by the speed of light, it gives us the distance in light years effectively. If it takes 1 billion years of time for that light to reach us, we can say it's 1 billion light years away, which is true. All of these distances, interestingly, are the same for very nearby galaxies out to redshifts of about 0.1. But once you get to very high redshift, they become more and more different, and it's more and more important to take that into account in when you quote a distance. Normally, distances in popular magazines and books and so on are what we call look back time distance, and that's why they never exceed about 14 billion light years, because you've only got 14 billion years of light travel time. 14 billion years since the Big Bang means you've only got 14 billion years of light travel time, so you can't get a so-called look back time distance bigger than 14 billion light years. But the distance now version of distance can be much larger than that, because over that whole 14 billion years the universe has been expanding, and those galaxies now could be much farther apart. The really weird thing is that because as you go to higher and higher redshift, you're going to look back times that are closer and closer to the Big Bang, at a certain point you get this distance then, the distance between the galaxies as light is emitted from 1, say, to ours, those distances actually start to shrink for higher and higher redshifts. They get smaller and smaller because the universe is getting smaller and smaller. And eventually, when you look back 14 billion years to the Big Bang, the then distances go to 0 because everyone was next door to each other in the Big Bang singularity. This also leads to a really strange effect in cosmology, where normally in the everyday world, as things get farther and farther away, they get smaller and smaller in size. It's obvious and logical. And it always reminds me of that famous sketch in one of those Father Ted episodes where Dougal has shown the little model cow and is comparing them to the cows in the fields in the distance. And you've probably seen this on the TV, and sort of translating between the small cow being nearby and the bigger cows farther away actually look the same size. Things get smaller as they get farther away. But interestingly, in cosmology, that only happens out to a certain redshift. And then as things get to higher and higher redshift, they essentially get farther and farther away in terms of distances now, or so-called proper distances. They actually start to get bigger in angle as well, because they were closer to us when the light left. So the angle that they correspond to gets bigger and bigger. Eventually, if you take that to the logical conclusion at the Big Bang, the light effectively comes from all around us. And that's sort of like, you can think of the microwave background coming from the Big Bang. Why is it all around us uniformly? Because its distance then was effectively very close to 0. So angles on the sky do really weird things in cosmology. When you get to very high redshift, galaxies actually start to get bigger again. Interestingly, though, the light still diminishes, and so their so-called surface brightnesses actually get very, very low, and that makes things harder to actually see. But that's another area where gravitational lenses start to help out tremendously by brightening those images again. So I hope that wasn't too technical, that bit, but it really does help. Well, it helped me anyway understand how we get different distances in cosmology, how we can get distances going all the way out to 14 billion light years of light travel time. Now, just as an example, we'll have a look at this remarkable image that was published in November last year, quite a recent discovery of a beautiful Einstein ring. This is one of the best Einstein rings discovered so far, and it was discovered by the ALMA telescope in South America, the Atacama millimeter array. And you can see the millimeter waves make up this beautiful ring of light in the sky. The lensing object in the foreground is a galaxy, which will be right in the middle because it's a ring, but that's invisible at these long wavelengths, interestingly, through this telescope at this time, and so that's invisible. We just see the gravitationally lensed ring. Remarkable, beautiful observation. If we measure the light of the ring with a spectroscope, we can measure its redshift. It corresponds to a redshift of 4.2. That's an enormous redshift. And that means the wavelengths of the lines in the spectrum are about 5 times longer than they should be if the gas making up that light were at rest. If we translate that redshift into a look-back time using cosmological equations, because that's such high redshift, not just simple Doppler formula, you get about 12.5 billion years. So that light has been traveling for 12.5 billion years. That's over twice the age of our solar system. In that time, the universe has expanded, and the distance that galaxy will be now, as we speak, is about twice that far, about 24 billion light years away. But when the light left it, effectively the universe was much smaller. It was only 4.5, I say only, it was still a ridiculously huge distance. It was 4.5 billion light years away when the light originally left that galaxy that we now receive. By looking at the light and the spectrum of that light, you can show that the type of galaxy that makes up that ring is a Milky Way type spiral galaxy, which was quite unexpected actually at such a high redshift. It's becoming quite difficult to actually form structures that we see at high redshift in the timescales that we have available, given that we've got to look that time at 12.5 billion years, and the universe, according to the Big Bang Theory, is 14 billion years. And we've only got 1.5 billion years to actually make an entire spiral galaxy and all the stars within it, and process heavy elements and so on that you see in the spectrum. So the timescale problem is starting, in a sense, to come back into cosmology as it was with a vengeance years ago, before people had really understood what the correct Hubble diagram was and so on. The lensing galaxy we can't see in the middle here has a redshift of about 0.26, corresponding to a distance of 3.5 billion light years. So again, relatively nearby lensing object. The very first gravitational lens to be observed was a famous twin quasar. Quasars are the very bright nuclear regions of active galaxies where we have a supermassive black hole absorbing gas and probably stars and other systems, generating enormous amounts of light as they go down the cosmic plug hole in the so-called accretion disk. And that light can be equivalent to all the rest of the stars in a galaxy put together. And so quasars were a great mystery for many years because they look like stars on the night sky. These two objects here are the twin quasar, and yet they have redshifts in their spectra that implies they're at cosmological distances, which are looking at redshifts again. The speeds are so high they couldn't possibly be stars. Normal stars just don't have those high speeds. We now know that they are actually within galaxies, and one aspect of the observations that showed these were indeed the same quasar was the fact they varied in brightness over short time scales, as quasars do. And each separate image varied in the same way, and the spectrum of light from each of these two images was identical in every way. And so it had to be the same quasar. And the only explanation was it was indeed the same quasar, but there's something in between us and the quasar that's splitting the light into these two images. And this system was observed in 1979, and it is the very first gravitationally lensed object that was observed. The galaxy, you can just see it in this image next to the more yellowy coloured quasar image here. That has a redshift of about 0.3, distance 4.5 billion light years. The quasar itself in the background, redshift 1.4, distance, look back time distance 8.7 billion light years. So again, very, very distant, as are all quasars. These very active galaxies were at their most active a long time ago in the history of the universe, and therefore we only see them at great distances or very high redshifts. The quasars are some of the highest redshift objects we've ever observed. They did hold the record for many years through the 1980s and 90s. Currently, in January this year, the highest redshift quasar was announced that beat the previous record and is now up to 7.6, a redshift of 7.6. That's an enormously high redshift, corresponding to an enormously great distance. Now, of course, it would be 20-30 billion light years away from us as we speak. There's evidence to suggest it has an enormous black hole in its core to generate the amount of light we can see from that thing, even though it's so far away. And again, that is such a high mass black hole, it's difficult to account for how such a massive black hole could form in the allotted time scale. So let's quickly get to the farthest thing we can see. The second highest redshift so far recorded was this galaxy discovered, I think, a couple of years ago in one of the very deep Hubble Space Telescope fields in a beautiful cluster of galaxy field. You can see here, this tiny little red spot here corresponds to a galaxy with a measured redshift of 9.1. That means the light has a wavelength 10 times greater than the light when it left the object. The universe is now effectively 10 times larger than it was when the light left that galaxy. The very highest redshift of all that's been measured to date is in one of the famous Hubble deep fields. This is a picture of the extension of the original Hubble deep field, the Hubble ultra deep field, this beautiful image of a small part of the night sky, equivalent to about 1/10 the diameter of the moon in the sky, but over an exposure of several weeks, building up the exposure, adding in the data to several weeks time exposure, you can see thousands of galaxies in that one tiny, tiny area of sky. There are similar deep fields now in different locations to confirm the universe is the same in all directions, or so-called isotropic. And this little tiny splodge was observed here in the Goods North field, which is another of the Hubble deep fields. And believe it or not, that when you enlarge that little speck, which you can hardly see in this image, to this little blob here, it can have a redshift measured with a very large ground-based telescope, and it corresponds to a redshift of 11.1. So that's the highest redshift we've ever measured for any galaxy. And this isn't a lensed object, interestingly. It's just an exceedingly faint object in one of the Hubble deep fields. Having such a high redshift corresponds to a light travel time of 13.3 billion years, 13.3 gigayears. So we're only a few hundred million years from the Big Bang itself for that galaxy. The distance it actually is as we speak is around about 32 billion light years away from us because of the expansion of the universe between then and now. When the light left it, the distance between it and us was only 2.7 billion light years, so roughly a factor of 10 between those two numbers. So I hope this talk has helped you understand the concept of distance in particular in cosmology, and how it's very difficult not just to measure distances to galaxies, but to even understand what those distances really mean when we're looking at tiny specks of light in an expanding universe. And because of the finite speed of light, we're not just looking out in distance, we're simultaneously looking back in time. So I think I'll finish on this remarkable, beautiful image of another Hubble Space Telescope deep field, one of the distant cluster deep fields, the Massive Cluster Survey, showing an extraordinary field of view full of stars in the foreground. Of course, the bright star-like images, there'll be stars within our Milky Way galaxy right in the foreground of the picture. In the background, we have a beautiful, massive cluster of galaxies, hundreds of galaxies within the cluster. And in the background, you can see a host of remarkable thread-like images of distant lensed galaxies. And again, it's by looking at this type of data that allows us to understand the history of our universe, essentially from the Big Bang to now. And as you can see, we've gone to from the here and now out to a redshift of 11. We've gone back in time over 13 billion years of history. We're looking at light that left those objects 3 times the age of the solar system ago. Absolutely remarkable. But interestingly, of course, we still have a way to go to get to the Big Bang itself. We have to fill in the redshift between those most distant galaxies we can see now with the Hubble Space Telescope and other big telescopes, and the so-called microwave background, where we know the first generation of stars should have formed according to our theories, and the very first galaxies should have lit up effectively out of the expanding structure that came out of the Big Bang. So I will finish there, and thank you all for listening, and I hope you're still all out there in the ether